Hello everyone, welcome to topic 7.11, Introduction to Solubility Equilibrium. By the end of this, you should be able to calculate the solubility of a salt based on the value of the KSP, or solubility product constant, for that salt. Let's keep going because Miss Burt needs coffee. Another application of equilibrium. So we've been talking about equilibrium prior to this. We're continuing with another application, is the solubility of solids. Not all substances are completely soluble or insoluble. So not all completely dissolve, not all completely don't dissolve or always precipitate out. Some are partially soluble. This means that they will dissolve to a slight extent. And the KSP we're going to see, or the solubility product constant, lets us see how soluble or how much might dissolve. The process of dissolution is reversible. The solid and aqueous ions are in dynamic equilibrium. We denote this type of equilibrium constant expression with KSP, where the SP stands for solubility product. The reaction is always written as a dissociation equation for the solid going into its aqueous ions. The solubility product constant therefore represents the maximum amount of ions that can be present in the solution before a precipitate appears. Remember that a precipitate, where's the pen? Is a solid. Okay, so for example, we have lead to chloride, and so when we write its dissociation equation, we show it splitting into its ions. Remember that subscripts become coefficients, and this is like a net ionic equation for that solid dissolving in water. Okay, so when we write the solubility product expression, it would be this. Notice we do not have any of the solid in the expression because solids and liquids are not included in equilibrium expressions. So the solubility product constant will never have denominators. Makes the math really nice. Okay, so there's no denominators when we're talking about solubility products, okay? The solubility product constant values indicate the extent that a solid will dissolve. Higher values mean that the solid will dissolve more, and lower values mean that that less of it will dissolve. So if we look at this exponent, negative exponents tend to favor reactants, if we remember that from equilibrium. Okay, so this means that it's going to favor the solid over the dissolved ions. So that means that this is not very soluble and is only partially soluble. If this was a positive 5, that is a very soluble because it favors the products strongly. Okay, and so the size of this indicates how soluble or how much will dissolve of that solid. Substances that are completely soluble, so our SNAP ions, the ones that are always soluble, sodium, nitrate, ammonium, and potassium ions, are not examples of equilibrium reactions. So like this one, for the dissolving of sodium chloride, it goes to completion because it's very, very soluble, because sodium is always soluble. The tables of KSP values are typically found in the back of your textbook. You can also find them here in this link. This is posted to Schoology, so you can find it easy. These are, if you need them on the AP test, they are given to you, or you are being asked to calculate them. Okay, and there are examples later. So don't freak out if you're like, I have to memorize how many different... No, it's given to you. You need to know how to use it or how to calculate it, given other variables. Okay, so there are a few types of questions that involve solubility equilibrium. You can find the solubility of the solid from the KSP value. So given this expression, we can let S, you can use X, it's just a variable. So S is like our X, but since we're talking about solubility, they're using an S instead of X. Make sense? So if we look at the mole ratio in the reaction, it's S to 2S. Okay, and so when you write the solubility product expression and substitute in for the ions, you end up with this, and so you take, you divide both sides by 4 and then take the cubed root of both sides to get this. So this is what is equal to S, and then you plug it back in to find the ion concentrations at equilibrium. Okay. Alternatively, you can do the reverse, and then this is also equal to the amount that'll dissolve. That S is the amount of that, or you can back calculate to figure out the solubility, not solubility product, but like solubility as in moles per liter of the solid that you're interested in, how much will dissolve. And then these two are the concentrations of the ions at equilibrium. Okay, and it's all based off of the mole ratios, okay, from the balanced reaction. Alternatively, you can do the reverse and find the solubility product constant given the solubility. So this here is the solubility because it's equal to the concentration of lead chloride at equilibrium, right? And then we can figure out how much lead ion and how much chloride ion by using the mole ratio. Okay, but we can also use that to figure out the solubility product. Okay, so for this reaction, AB3 yields A to 3 plus B 3B minus, writing the KSP here. Okay, and since we know that the solubility or the molarity of A is this, the molarity of B has to be 3 times that because of the mole ratio. Okay, so you would multiply it by 3 to get it. And so then when you multiply all of these together, you get the solubility product constant. And we're going to work through some examples of it, so don't freak out. There's pre-worked examples, and then we're going to go through some normal ones. Because different compounds have different ratios of ions, you can't compare KSP values to determine the solubility unless they form compounds in the same ratio. Okay, so like you can't compare the solubility of lead to nitrate to aluminum phosphate because they form in different ratios. Okay, because it's like 1 to 2 versus 1 to 1. But if you had ones that had similar ratios, you could compare their KSP values to figure out which one's more soluble. Okay. A lot of these types of questions tend to be scaffolded on the AP tests, so you aren't being asked to do like big, lengthy calculations. Okay. So, because everything's 1 point, and so they need to be able to break it down to figure out, based off of the steps needed, can you get through the chemistry? So it's usually a bit more scaffolded than you might see on some practice questions. Okay. So looking at this, the compound XBr3 has a solubility product value of 4.52 times 10 to the negative 8. When XBr3 is added to water, what is the concentration of the X3 plus ion and Br minus ions? So the first step, your first step is to always write the, for this one, you need to actually write the dissolution equation. Your second step is to then write the KSP expression, and so that's X3 plus, and then for this, you know that this should be S and then 3S. And Miss Burt, where are you getting that? Well, if we go back to our ice table, we know that this one doesn't count because it's a solid. These two, before we start dissolving anything, are concentrated at 0. So we're going to make in their coefficient ratios those. Since it's solubility product, we can use the variable S. If that is confusing or looks too much like a 5, use X. And so this becomes S and 3S. So that's where those come from. But because it's solubility product and it's always going to be in a very specific format, we can skip the full ice table setup and just simplify it by representing S and 3S. Okay? Good so far? Do you want me to pause? Okay, back on track. So finishing our solubility product expression, we then write our anion, and that is cubed. So it's always products over reactants to the power of their coefficient. Since our reactant is a solid, we do not include it in the expression for solubility products. So it is just the product of our products, multiplying our products. That is a lot in my mouth. Okay, so now we can substitute in for the values we know. We know that KSP is 4.52 times 10 to the negative 8, and this is equal to S times 3S cubed. Simplifying this further, we have 4.52 times 10 to the negative 8 is equal to 9S to the 4th. When solving these, you have to work the order of operations backwards. So you don't do exponent. You normally would solve exponents first. You need to save those for last because you have to undo the least priority first before you get to the highest priority. So you first divide by 9, and that gives you a number, and I definitely did not solve that. So it gives you some number right here is equal to S to the 4th. And then you're going to take the 4th root on both sides. And you should get that S is equal to, bless you, 8.42 times 10 to the negative 3rd. And since S is a unit of concentration, we have molarity for its units. Okay? So now when we look at the concentration of the two ions at equilibrium, we substitute the S into their equilibrium constant or expressions. So X3 plus is just going to be 8.42 times 10 to the negative 3 molar. And then the bromide ion is going to be 3 times that, which is 2.53 times 10 to the negative 2 molar. This actually shows you why you should use a calculator. This should be 27. So you're going to divide by 27. And then you get a number. I think it's somewhere around 5 times 10 to the negative 9. Somewhere around there. And then you take the 4th root of both sides. And you get numbers. So this should teach you guys to not listen to Miss Burt. This number right here is, wow, I got off on that one. 1.67 times 10 to the negative 9. I can't do math, apparently. And then when you take the cube root of that, you end up with 6.40 times 10 to the negative 3. So that's your S, and wow, that was off. I'm pretty sure that when I did the original math, I did not do the 27, which would make sense because I made the same mistake twice. 6.40 times 10 to the negative 3 for that one, and then you multiply that times 3 to get B, and holy Jesus, that was off. 1.92 times 10 to the negative 2 molar. Now we have the right answers. Woo! Who feels better that they are not the only ones who mess stuff up? Okay, now we're going to try a we do, and we're going to go through this in steps. So, will a precipitate form if 120 milliliters of a 0.1 molar magnesium nitrate solution is added to 440 milliliters of a 0.00450 molar sodium hydroxide? So magnesium hydroxide, that's going to be the one that's your solid forming, is 5.61 times 10 to the negative 2. So our first step is to write the dissolution equation, the dissolving reaction for magnesium hydroxide. Please pause the video and do that now. Okay, so you should have gotten this equation. Now, since we are mixing two chemicals, this one is a little tricky. Okay, you have to determine the new concentrations of the original solutions after you mix them. So we know the original concentrations, which are here, but we have two volumes that are being added together. Okay, so we're going to do the one for magnesium nitrate together, and I'm going to ask you to then do the one for sodium hydroxide on your own. So what would the total volume of our new solution be? So our new volume, or volume total, is what? 560 milliliters. Okay, so for the magnesium nitrate solution, we're going to take, it's a dilution equation, right? So M1V1 equals M2V2. Okay, so M1 is 0.100 molar times V1. And you can, since they're both in milliliters, you can leave them in milliliters because they'll cancel out. M2 times V2 is 560, and that's in the way, milliliters. Okay, that's 560 milliliters up here in the top. So you're going to solve for M2. And you should get, somebody please check my work, 0.0214 molar for magnesium nitrate. Cool. Okay, using the same process, the dilution equation being your best friend in this scenario, I want you to figure out the new concentrate. Pause the video and figure out the new concentration of sodium hydroxide. Same process. Go. So after running the calculations, you should get that the concentration of this solution is 0.00354 molar. Okay. So these are the concentrations of the two ions when we mix them in solution. Or the solutions, when we mix them, those are the concentrations. So when we are looking at if they're soluble, we're going to compare the Q to the K because we need to figure out which direction the reaction's going to shift. Okay, when it's asking, is a precipitate going to form, calculate Q and figure out which direction it's going to shift. Okay, so we're going to calculate Q. So this was our second step. Our third step is to calc Q. And so we need to figure out what our ion concentrations are. So the concentration of magnesium comes from the magnesium nitrate. Well, since it's one magnesium from one magnesium nitrate, this is the concentration of magnesium in the total solution. So this is 0.0214 molar. And then for the hydroxide, we look at the original solution. There is one hydroxide in the sodium hydroxide solution, like compound. So it's a one hydroxide to one compound. So this is the concentration of it. We don't have to multiply by a coefficient or a number because there is no subscript. Okay? So is 0.00354 molar. Okay. Are we stop it? I don't know what happened. Anyways, okay, so Q, or the K expression, right? They're the same, it's just different points in the reaction process. For this is the product of magnesium ion times the product of the hydroxide ion concentration to its coefficient. Since we know those concentrations, we are going to plug them in and figure out what Q is. So 0.0214 times 0.00354 and somebody working the maths after me, I got 2.68 times 10 to the negative 7. Yeah? Okay. So we now compare Q to K. So Q, okay, so Q is bigger than K, right? We look at the exponents here. If the exponents are equal, then compare the numbers out in front. Okay, but since negative 7 is much bigger than negative 12, right? That negative sign means you have to pay attention, right? Negative 7 is bigger than negative 12, right? Okay, try writing it out. Negative 7 power is much easier to write out than negative 12. Neither one is fun. So Q is much bigger than K. That means that your products are in higher ratio to your reactants. So you have too many products at this point in the reaction compared to your reactants. Granted, our reactants are like solids, but this tells us that a solid's going to form. That the reverse reaction is favored. And then a precipitate, PPT, is like a standard notation for precipitate. Okay, so this concludes the 7.11 notes. The you-dos continue. You probably can watch this at like 2 times speed, but you know, check your work and thank you for tuning in.